Welcome to the AI and GIS Frontier podcast. Let's get into today's topic.
Today, we are covering deep learning for satellite imagery. This is the engine behind so many of the applications we have discussed on this show, from forest monitoring to disaster response, and the technology is advancing fast.
What are the big breakthroughs in the past year?
The standout development is unified models that can predict multiple variables simultaneously from a single satellite image. There is a new model that takes multi-sensor, multispectral imagery at 10-meter resolution and predicts above-ground biomass density, canopy height, and canopy cover all at once, with uncertainty estimates for each. For a forester, that means one model run gives you the three most important stand metrics instead of needing separate models for each. And the uncertainty estimates tell you where the predictions are reliable and where you need field verification.
How does that change the forest inventory workflow?
Dramatically. Traditional forest inventory involves sending crews into the field to measure sample plots, then extrapolating across the landscape using statistical models. It is expensive, time-consuming, and gives you point estimates, not wall-to-wall maps. With these deep learning models applied to freely available Sentinel-2 imagery, you get continuous maps of biomass, height, and cover across your entire management area. Field crews then focus on validation rather than primary data collection. A forest district that used to budget 6 weeks for field inventory might cut that to 2 weeks of targeted ground truthing. The cost savings are substantial, especially for large management areas in remote boreal or mountain forests.
What about change detection? That seems critical for monitoring.
Change detection has gotten incredibly sophisticated. New architectures can identify not just that something changed, but what kind of change occurred. Is it a clear-cut, selective harvest, blowdown, insect damage, or fire? And they can do it at sub-hectare resolution. There is active research on physics-aware diffusion models for LiDAR point cloud densification, which means you can take sparse LiDAR returns and generate dense, three-dimensional forest structure data. For forestry operations that use LiDAR for harvest planning, this means you can get useful structural information from lower-cost, sparser acquisitions.
YOLO models are being adapted for satellite data now.
Yes, YOLOV 8 and V9 have been adapted for object detection in very high-resolution satellite imagery. The immediate applications are infrastructure monitoring and vehicle detection, but for environmental work, people are using them to detect individual trees in open canopy forests, count wildlife in aerial surveys, and identify illegal mining or logging equipment in remote areas. A conservation organization monitoring deforestation in the tropics can now automatically flag heavy equipment appearing in satellite images near protected areas.
What about the environmental monitoring applications beyond forestry?
Land use and land cover classification keeps getting better. New models on the Eurosat benchmark, which has 27,000 images across 10 land cover classes, are achieving accuracy rates that would have been considered state-of-the-art for medical imaging just a few years ago. For watershed management, deep learning is being used to track riparian vegetation health over time, detect illegal encroachments into protected stream buffers, and model sediment transport based on upstream land cover changes. For wildlife agencies, automated habitat classification at landscape scale is becoming routine rather than a specialized research project.
What should a GIS professional know about working with these models?
The most important thing is that you do not need to build these models from scratch anymore. Pre-trained models and transfer learning mean you can get excellent results by fine-tuning an existing model with your local data. Tools like TorchGeo and TerraTorch, which we will cover in another episode, make this accessible to someone with basic Python skills. The workflow is find a pre-trained model close to your use case, collect a modest set of training samples from your area of interest, fine-tune, validate, and deploy. A forest analyst who has never done deep learning can produce a high-quality species classification map in a few days with these tools.
Where is this heading?
Real-time monitoring is the end game. With daily satellite revisits from Planet and upcoming hyperspectral missions, combined with edge computing on the satellites themselves, we are moving toward continuous Earth monitoring. A forest fire starts, and within hours, you have an AI-generated damage assessment. A landslide blocks a logging road, and the detection is automatic. Insect mortality spreads through a stand, and the early warning comes from the satellite before a field crew would notice. The deep learning models are ready for this. The satellite infrastructure is catching up. Within 2 years, near real-time environmental monitoring will be operational, not experimental.
Exciting future ahead. Thanks for the deep dive into deep learning for satellite imagery.
Thanks for having me. The key takeaway is, The barrier to using these tools has never been lower, and the capabilities have never been higher. Now is the time to dive in.